So this notes video will be on composite transformations, and the reason why I have a picture of Mario here is because Mario and the other characters in the Nintendo game undergo composite transformations as you play the game. Mario will translate as he walks, he'll also reflect to turn around, he'll dilate when he eats the mushroom and grows bigger, so just an example of composite transformations. So the definition of composite transformation is when a sequence of transformations takes place, which sequence would be more than one, and order does matter. It's very important to recognize that order matters in composite transformations. And pause this video if you need to copy down that definition, or you do need to, so make sure you pause it and get that down. And we're going to look at two examples when order would change the result of the composite transformations. So the first one is a translation of 3, -5. So we're starting with the purple triangle. We're just calling it A. And if we translate 3, -5, that would be 3 to the right, and then 5 down. So we end up here at A prime. And then the second transformation that it's undergoing is reflecting over the y-axis. So after it's translated, then it's reflected over the y-axis, and we end up with A double prime. So, A double prime comes from A prime. In the image of that, A prime prime, we just read it A double prime. So let's look at that those same two transformations, but in a different order. So if we look at first reflecting over the y-axis, our A ends up at A prime over here. And then if we translate with the vector 3, -5, which would be 3 to the right and 5 down, we end up here. Now, those are not the same location, so it's very important that you realize that order does matter. Okay, so we're going to recall composite functions from algebra. You may or may not remember this. This little symbol, this O is, circle is how we would note composite functions in algebra, and we're going to use a similar notation for composite transformations in geometry. So you would read this f of g of x, and you would read it the same here, f of g of x. So whenever you're doing these functions, you would always work from the inside out. So you would plug g of x into f of x, and you would evaluate this part first and then move out and evaluate the function f. So if you don't, really recall that from algebra, the main part that you want to remember is that you're working from the inside out. So you're always working with the second function listed, and then you move outward to the first function listed. So evaluate the first, and then evaluate the second. So interpreting this notation in geometry, we have the circle again right here, and this means that we're performing the sequence of transformations starting with reflecting over the y-axis. So that's what we're going to do first. We're working from the inside out. We're going to reflect over the y-axis first, and then we will translate -3, 5 second. So we're always working from the right side over to the left side, inside out. So we're going to look at a composite transformation and doing it. So looking at the notation, we want to recognize that we're working from the inside out, so we're going to be reflecting across the x-axis first. I know this is a reflection because it has a line listed, And the second thing we're going to do is rotate about O, which we have a coordinate plane, so that's the origin, and we're going 180 degrees, and that would be counterclockwise. So when we actually do our composite transformation, we're going to do both of them. We need to reflect first and then rotate second. If we're reflecting over the x-axis, we will end up here. So if I count my distance, that A, B, and C is from the x-axis, those distances are replicated to get A prime, B prime, and C prime. I want you to make sure that you have this example. So we may not have drawn both of the transformations in different order to show that, but I do need you to have this example. So first we reflected. If we look back up at our notation, then we're going to rotate 180 degrees. And the way I'm doing that is I'm going to write down the ordered pairs because I'm leaving off at A prime, B prime, C prime. I've written down the ordered pairs, and I'm going to apply the rule that we learned goes with 180 degree rotation. So that rule is negative x, negative y, excuse me. So I'm going to plug my pre-image points into the rule, and I'll get my image. So I'm basically changing the sign of both the x and y value, and I'm not rearranging them, switching their order. So my positive 1 for x becomes a negative 1. My negative 1 for y becomes a positive 1. And I've gone through all 3 points, just switching the signs for both of them because that's what the 180 degree rotation rule is. So after I have found my A double prime, B double prime, and C double prime, I've graphed it over here. So this would be our final answer for the composite transformation. First, I reflected over the x-axis, and then I rotated 180 degrees. Okay, so now we have another composite transformation. First, we're going to reflect over the line y equals 1, which I've put in blue here to match the color coding up top. And then we're going to do the reflection over y equals negative 1 second. And I want you to notice what relationship do these two lines have right now. As we do the composite transformation, I want you to pay attention to. Think about that right now. What relationship do these two lines have right now? So if we reflect over y equals 1 first, I need to count the distance that each point is away from my blue line, y equals 1. I see that both z and y are 2 spaces away, so z prime and y prime also need to be 2 spaces away. And then x is 4 spaces away, so x prime also needs to be 4 spaces away. So when I reflect my z prime, x prime, and y prime, or x prime, y prime, z prime, I need to be the same distance away from my blue line, which was y equals 1. And I see that I have 2, 2, and then 4. So I do have those same distances. So now our second reflection that's going to happen is reflecting over y equals negative 1, which is our red line. So both z prime and y prime are on the line of reflection, so their images will also be on the line. We know that if a point is on the line of reflection, then it really doesn't go anywhere. So I'm concerned with the distance that x prime is away from the line. It's 2 spaces away. So my x double prime would be up 2 spaces away, flipping back over this red line. And so in green, I have my final composite transformation image, x double prime, y double prime, z double prime. My x double prime is 2 spaces away, and both z double prime and y double prime are on the line of reflection. So I want you to look at how the final image, x double prime, y double prime, z double prime, I want you to look at how that final image compares to the pre-image. So we're comparing x, y, z and x prime, y prime, z prime. and I want you to, it's kind of cut off right here, but what one transformation could have taken place. So just to get from the pre-image to our second image, so from here to here, what one transformation could have taken place? Instead of doing it twice and doing a double reflection, what one transformation could have taken place? So you may have thought that a translation could have taken place. The triangles are sitting the same way. Their orientation didn't change. So you know that's the big deciding factor when you're seeing if it's a translation. The orientation has to stay the same. So we see that the triangle is facing the same way. It's just in another location. So it's actually just moved down 4 spaces actually. So the final thing that I want you to write in your notes is that, and back to the 2 lines, which I asked you about earlier, you should have noticed that these 2 lines are parallel. They both have a 0 slope. They're horizontal lines, so they're actually parallel lines. And so something that we need to note is that if we are doing a composite transformation of 2 reflections over parallel lines, we can always do this in one translation. So when we reflect it twice over that horizontal line, or it could be a vertical line also, we'll flip the orientation, but then we'll flip it back to the original orientation. So you could always shorten a double reflection over parallel lines by just doing one translation. I want you to make sure that you have this noted. So that's it. Once you have that down, that's it for our notes on composite transformations, and I will see you in class.